talk logarithmic functions. This is actually the third video I shot, so I'm about to repeat some information, or at least some advice. Please know at this point I'm not expecting you to be an expert on logarithmic functions in the same way I don't expect you to be an expert on cubic or rational. That's not exactly what I'm testing. What I'm testing and what I'm going to ask you to be an expert on right now, or at least notice right now, is that when you look at a function like a logarithmic function, cubic or rational, there's a set of basic information that you should be aware of and in your head should immediately jump to. And so if you notice kind of if you watch my other videos, or maybe if this is your first one, if you think about the last activity we did in class, where I had you guys pick up a different colored pencil and kind of add to a single sheet over and over again, these functions these analyses are asking you to do the same questions over and over. It's the same questions I asked you like on the second day of class to analyze those functions. I'm asking the same things over and over again. And so I'm trying to embed in your head is like when you look at these functions, you should immediately snap to a certain volume of information. Like you can call this a function analysis because that's what a lot of the math community would as well. And so it's the same questions you should ask yourself if you're talking about linear or quadratic or logarithmic or exponential, whatever I give you. You should immediately start thinking about what's the general function, what's a parent graph, what's a parent graph look like. All this stuff is what you should have in your head. Now the question is not really a question at all. It just really says logarithmic functions, all of it. And so like I'm probably going to ramble on for a while because I don't know exactly what information you really need. So in the future, if you be more specific, I can give you a more specific overview. But with that being said, let's talk a little about logarithmic. Let's see if I can give you a better basic understanding of it. And then maybe this information or these questions I'm asking you will make more sense. So what I actually want to do is go to the Desmos graphing calculator. I think that's where we're going to gain the most traction right off the bat. So let's go ahead and graph the logarithmic paired function right now. And so let's start with f of x because we need to start with a nice function definition. So we'll take the log, and now it's going to look weird because I have to actually write the word base here to actually pick a base. But let's just pick base 2, and then I actually have to back that off and delete it, of x. So like we now have a nice graph right next to it. Now Desmos.com, that's the site I'm on right now. If you never have used Desmos too much, make it your best friend because it's going to be. We're going to use it a lot in class. It's something that's going to really help us understand graphing behavior over time very quickly. So let's get to it. So the first thing you notice that this is not a regular looking function. So if you've been dealing with quadratic, linear, and cubic, which has really been a lot of your algebra experience so far, this is very different. The function itself is not defined as a polynomial. It's defined to be like this weird log. And I'll explain what that means in a second, but I just want to talk about some behavior first. So one thing that's important is thinking about end behavior first. And all end behavior is if I go to the maximum x value, what is the y doing? If I go to the minimum y of x value, what is the y doing? And again, like that's all that end behavior really is. Just like what's happening as the x gets very, very large to one end of the domain, and what happens when x gets towards the other end of the domain. And so we can do that here simply by dragging the graph. So as x goes to the right, if you notice this function is increasing. There's a common misconception that with logarithmic functions, as the x goes to one end of the domain, there's actually a horizontal asymptote. There's actually going to be like a maximum value that it reaches, or minimum, maximum value that it reaches, and that's really not the case. If you look, it's still increasing. It's increasing slower and slower, which is a benchmark of logarithmic functions, but there isn't actually a maximum value. If I continue that all the way out, that will actually reach positive infinity. Now, if I go to the other end of the domain, though, as I go towards x equals 0, there is something interesting happening. There is an asymptote, a vertical one. In other words, it's a value of x that this simply cannot reach. And when you have a better understanding of the function itself on the left, this will make a whole lot more sense. So we can see the function diving down, and so as I'm reaching this, a value of x equals 0, which I'll graph right here, x equals 0. As I'm reaching the blue line, you can see this is getting very, very close to it. Now, it almost looks like they're the same line, and that's simply because like the resolution on my computer is not good enough to differentiate it. But there actually is a barrier there. It cannot actually reach 0. So there is a vertical asymptote at 0. Now, if you go over here to the function, it makes sense there is a vertical asymptote here, and if you understand how to read this function value. The way to read this, and I'm going to replace the f of x with a y here just for a moment. The way I understand this, the relationship between x and y is this. If I take 2 to the yth power, I should equal x. Now that's weird, especially if you haven't had a ton of experience with logs. I know that sounds unusual, so let me try to explain it and then I'll demonstrate it for you. And so the way to relationship x and y through a log is that 2 to the yth power equals x. So I'm going to flip this to the table view and let's see if it makes some sense out of that. So we have a lot of things that are defined. So remember, it's 2 to the yth value equals x. So 2 to some power equals x. Well, if let's say I want the x to be 4, so I have to think like 2 to what power makes it 4. Now, if you think about that, pause the video if you need to, but 2 to what power equals 4 is 2. And so if I define the x to be 4, we actually have a log value of 2, and we can actually confirm that by clicking that here on the graph. So again, let's think about this. Let's pick another power of 2 that we're aware of. Let's say 8. So 2 to what power equals 8? 2 multiplied by itself, how many times equals 8? And the answer here should be 3. And then we see pop up. So again, here we can go to 8. We can notice that if I take 2 to the third power, it equals 8. 2 to the y equals x. If we take like 16, that's going to be 4. We have 1 here at 0. It looks like we have 1 here, 2 to the 1 power. Because again, 2 to the first power equals 2. Now, this should make sense then why we can't have 0. 2 to what power is 0? Okay, now if you say 0, do recall 2 to the 0 power is 1, which is why we have this thing here. There is no number that you can multiply to end up, there's no power, that you can take 2 to make 0, which is why you actually have an asymptote right here, okay? So when you think about logarithmic functions, that's like the one basic thing you have to really consider, is that it behaves very differently. So it doesn't play by all the same rules. If I flip back over here to my page, and you'll have to excuse me for a second, my computer is about to die and I want to lose this video, so give me a moment to get my computer plugged in. All right, and we're back. So now we can actually start examining, now we can start examining some of the, let's say, particulars. If we look at the general logarithmic function, you already saw me type in an example, and that example is actually the parent, which I'm going to write up here. So we can actually identify the parent as, say, something like f of x equals log base 2 to the x. That's not the general function, though, because there's a lot of things that can modify this function, but these are not going to be new things to us. If we think like back to Algebra 1 and all the ways like an equation can be modified, so can this here. And so although we're definitely going to have like the log, and I'm going to use a to the x power, we can have a coefficient. We can have a number that we multiply by 2 out in front. Actually, let's change this to b, just so we have a nice symmetry here. So we can say like the leading coefficient here is a. We can take the log base to be b. That makes more sense anyway. And then we can also have a scalar addition or subtraction, which I'll call c. This is actually going to be all the pieces that you could add to the function, which is why it's a general form. Remember, the parent form of a function is just the simplest version. And so like the parent version is just when a in this case equals 1, b is the lowest value it can be, which is 2, and c is going to be 0. If we flip back just for a moment to Desmos, we can actually test this. Oops, come back here. Okay, so if we take like f of x, and again, let's make it log base 2 of x, okay? We can start adding those other pieces. So like, if we want a to not be 1, let's say we want a to be 3, that's what happens to our function. If we want it to be like, let's say, negative 0.5, all it's going to do is kind of change the way our log moves around. And this is, again, should not be new information. We're going to explore, of course, all this much more in depth later. This is just the basics. We can also add like a scalar addition. Let's move this back to a positive value. Okay, so like if I just throw an addition problem at the end, let's say I want it to be like, oops, let's say like plus 2. That just means I'm moving my function up. Let's say I make it plus 3, plus 4, plus 5, plus 1. You're seeing like this function is just kind of moving about. Bringing back to 0 right back there. So when you think about a general function, like all general functions, it just represents using variables all the numbers or places numbers could go that will further modify the function from the parent. So the parent is simple. The general function is going to be is going to identify all the things you could do to the function. Now some of these terms don't necessarily make sense to the general function. Like argument does, because argument is one of those things that applies to all functions. The argument is simply going to be the independent variable, the IV. The argument, in other words, is just the x. It's the variable you put in that helps you actually define the function. It's the one that you choose. The degree of the function makes no sense here because logarithmic functions don't have a degree. They're not polynomially defined. So leading coefficient doesn't really make much sense here. I guess you could technically say A is leading coefficient, but it doesn't really make a whole lot of sense here in this context. In terms of variable terms, well, that does make sense because variable terms are the ones that contain the variable. And so like, that would be the variable term, and constant term, well, that's the one that just has the constant, no variable. That's your constant term. Okay? Like this is a picture. This is not the parent function. We know it's not the parent function, by the way, because the asymptote has moved a little bit to the left, and also the 0 is no longer a 1. Recall 0 just means where it crosses or takes a value of 0, y equals 0. So in this case, our x-intercept, which is synonymous with 0, is going to be 3, 0. That was weird. In terms of asymptotic behavior, we identify there is no horizontal one, although a lot of people think there is. But there is going to be a vertical one right here. Wow, that's much thicker than I thought it would be. There it goes. Okay. That's your horizontal asymptote. And so that's going to be actually x equals, looks like 1. We have a y-intercept as well, which because of the way the function's written, it typically doesn't have a y-intercept. But this one's been shifted around a little bit, and so it's worth noting that this one does here at 0, comma, looks like what, -1? Where this thing here was a 0. Okay, oops. We talked end behavior on the parent graph, so it's worth mentioning here again. Keep in mind, parent end behavior should not freak you out. It's just talking about not the kind of part in the middle where all the action's happening, but what happens as x goes to one end of this domain or the other, just what's going on. And we can identify that by just writing a quick little statement. So in this case, as x approaches the far end of the domain, which is infinity, y approaches the far end of the range, which is, in this case, infinity. On the other end of things, on the left here, as x approaches its maximum value, and in this case, since there is an asymptote, the maximum value is, whoa, I messed that up. That should be -1. No one caught that. -1. Okay, so as x approaches -1, which is its max or minimum, x value, y is going to approach the minimum part of the range, which is -infinity. Okay, which is how you can ultimately identify the domain and range. So if you watch my other video, I'm going to repeat some information here. I don't care how you write the domain and range, to be honest. I know from my experience at the collegiate level, the set notation is very common. Interval notation is fine. Like, it tends to make more sense. I just don't think it's used as much when you get into those higher level math classes. But either way, domain, we're talking about all the usable x's. Now, if you identify end behavior, this is actually a really easy part because you already identified where your domain and range are. So your domain in this case is defined to be the x values, such that, and let's use inequality notation and side set notation, where it's going to be less than infinity, but it's also going to be greater than -1. Now, note here that you cannot reach -1, which is why I'm not doing that. That line underneath the inequality, that thing right there, indicates you can use -1, but you can't here. In terms of interval notation, we use a curved bracket to indicate you cannot use a value. It starts at -1, ends at infinity, unbroken, and so we'll cap it up there. For the range, if you go back here, notice the range was actually all the values. So this one's actually going to be quite a bit easier. We can use all y values so that y is actually less than infinity, but still bigger than -infinity. In terms of the bracketed notation here, the interval notation, we can't reach -infinity, we can't reach infinity, but we want all the numbers in between. Um, we played a little bit on decimals about the different end behaviors. I'm not going to go over that again, but that's really all you really need to know about logarithmic functions. If I didn't hit the question you intended, try to write a more specific one. I'll try my luck at it again. If this helped, hopefully it did. If you know a friend in class that would help, have them watch the video. Otherwise, come work with me, Math Lab 4A. You can actually Math Lab any hour of the day. Also, before, after school, especially B days before school, and after school any day but Monday. So get the information you need so you can be successful. Guys, I hope that helped. I'll see you later.